Here talking about delta G and favorability. What we talked about last time was standard conditions, and now we're going to talk about what to do when we're not at standard conditions. So standard conditions would be 25 degrees Celsius, 298 Kelvin, and 1 atmosphere. So sometimes we're not going to have it exactly at room temperature, which is 25 degrees Celsius. So we can change delta G by multiplying by a different temperature in the delta G formula. However, you cannot use your delta G not tables. So don't use this. You can't do products minus reactants, okay? Because this little symbol means it's standard. So you want to make sure that if you're not at 25 degrees Celsius, then you're not using this and looking up the values on the table. You have to use the formula. So here's just a little explanation of why we can actually do that. Delta H and delta S are not very temperature dependent. So we can just use the equation and change T. Okay. So we've done delta H and delta S for this already. So here are those values here, okay? And we're going to use the formula to find delta G at 1400 Kelvin, okay? Remember that your temperature, although we did say 25 degrees Celsius a few times, your temperature for the delta G formula has to be in Kelvin, okay? So make sure you're using Kelvin temperature, and that's because your S will be joules per mole Kelvin or kilojoules per mole Kelvin. Okay, so if we just plug in our new numbers here, delta G is our delta H minus, and then T, remember it's in Kelvin, so 1400. And then don't forget, just like in the last video, if the delta S is in joules, you have to convert it to kilojoules. And a lot of times delta S will be in joules. So always make sure you check your delta S unit. And when you get that, do that out. So this reaction at 1400 Kelvin is favorable. Okay? At 298 Kelvin or 25 degrees Celsius, it was not favorable. It was not thermodynamically favorable. So the temperature obviously changes the favorability. Okay? So here's just a little bit more about this reaction. It was not favorable at room temperature. It came out to 140 positive kilojoules. It is favorable at 1400 Kelvin. So then there's the question, at what temperature does the favorability change? And to figure that out, you're just going to set delta G to 0. Just looking to see if we do that on the next slide. So if you set delta G to 0 and solve for temperature, then you can figure out what temperature that goes from positive, unfavorable, to negative, favorable. So if we set delta G equals 0 and keep our delta H and delta S the same that we've been using for all of them, so positive 196 for delta H, we're going to solve for T here, and our delta S converted to kilojoules is this. So when you solve for T, you get 1026 Kelvin, which if they want it in degrees Celsius, you know how to do that. Okay, so that is the temperature where we're switching from favorable to unfavorable or vice versa. So let's talk a little bit about what delta G equals 0 actually is, okay? it will seem like the reaction stops, but you've already learned that that's not true. What will actually be happening is that the reaction will be at equilibrium. So the forward reaction will equal the reverse reaction. So to the human eye, it will look like it stopped. Okay, so if delta G is 0, then the reaction is at equilibrium. So we already know about delta G. If it's negative, it's thermodynamically favorable. If it's positive, it's not thermodynamically favorable. And again, all that means from the last video is that the products are not favored in the reaction. At delta G equals 0, we're at equilibrium. There's no net movement. So the rate of the forward reaction is equal to the rate of the reverse reaction. We know from our prior units that that doesn't mean the reaction actually stops. It just means that whenever a product is converted to a reactant, a different reactant is converted to the product so that the rates are the same. Okay, so take a look at this one. These are the types of conceptual questions you might see in multiple choice. The reaction below is not thermodynamically favorable at 298 Kelvin. Without making any calculations, is there a temperature at which this reaction can become thermodynamically favorable? These are very typical questions for delta G. So you know, in order for it to become favorable, we need this to be negative, okay? And they tell us here that delta H is positive and delta S is positive. So what that means is if we increase this temperature or if we decrease this temperature, can we make delta G negative? So it's just a mathematical, conceptual thinking through it, okay? So if we know delta H and delta S are both positive, if we make T big enough that it kind of wins this equation, then we will have a negative delta G, okay? We don't need to know what that number is because we don't have enough numbers to figure that out. The question is just a conceptual question. Could we do it? So the answer here is yes. Increasing the temperature will make the reaction favorable because then the negative will win out in that little subtraction there. So let's take a look at another one of these types of conceptual questions. Okay, so this one tells you that delta H is negative and delta S is negative. So if we do our conceptual analysis of our delta G formula, this is negative and this is negative. So we know that since it is a subtraction, right, this would make the second part of the subtraction positive. So when we think about which one we want to quote unquote win here, we want delta H to win. We want delta H to be the bigger one because that would make delta G negative. So if delta H is the bigger one, we have to make this little contraption smaller so delta H wins. In order to do that, you just make temperature lower. Okay, so the question there is, the answer there is, we would decrease the temp to make it favorable. And so you'll notice in both of these questions, one of our either delta H or delta S is favorable. And so T will make a big difference, okay? So here, we know that delta S, when delta S is positive, it's favorable. So our delta S is favorable here. So we have to make this one bigger, okay? So it's like whatever one out of these two is favorable, you want to make that one bigger. So here, if delta S is positive, that's favorable. Delta H is positive, that's not favorable. So we want to get that to be lower. And then here, delta S is negative, which we know is not favorable. Delta H is negative, which we know is favorable. So it goes back to that whole stuff that we've been learning in this unit about what's favorable and what's not. And so here, because delta H is the favorable one, we want to make that one the bigger one. That one's going to win. So we'll make temperature lower here. But now let's take a look at this one. For this one, delta H is positive and delta S is negative. Both of those are unfavorable. So we know delta H is negative is unfavorable. Delta S is negative is unfavorable. There is no, delta H is positive is unfavorable. There is no way to make this come out to a negative delta G. No possible way. Because changing the temp will do nothing if they're both unfavorable. On the flip side, if they're both favorable, then there's no way to get it to be unfavorable. The temperature really doesn't matter there either. So if they're both unfavorable, there's no chance we can fix that problem by changing the temperature. Okay, so here's a little bit of a look that kind of summarizes what we were just talking about. Okay, so this formula is Kelvin, you know this is always going to be positive. So it really just comes down to delta H and delta S. So here's a nice little chart that would be helpful. If both are favorable, we said it's delta G, the reaction will also be favorable. If both are unfavorable, then there's no way to make it favorable. And then here, if we have unfavorable delta H, but favorable delta T, we want a higher temperature. And if we have favorable delta H, unfavorable delta S, we want a lower temperature. Okay, so this is really just summarizing those conceptual things we just went through. So now let's take a look here. At what temperature is this process at equilibrium? What temperature does ice melt? What temperature does water freeze? 0 degrees Celsius. Okay, so if no heat is transferring there, so it can do either one, right? It all comes down to heat transfer. But if no heat is transferring, it's going to be at equilibrium, where some gas molecules will turn into liquid and some liquid will turn into gas, but they're going to be at the same rate. When a substance is at its normal boiling or normal melting, usually freezing temperature, it is at equilibrium. Normal means at 1 atmosphere. So whenever you hear normal boiling or normal melting, it's 1 atmosphere. That's what normal means. So at equilibrium, delta G equals 0. So if you have it at its normal boiling point or normal melting point, the delta S of melting or boiling will just be delta H over whatever that melting point or boiling point is. So this will come in handy sometimes because we can set delta G to 0 at these boiling or melting points, because like we saw up here, it will be at equilibrium as long as no heat is being transferred. So here, the molar heat of fusion delta H is 6.01 kilojoules per mole. In which expression do we get the molar entropy delta S in kilojoules per mole for ice at its normal melting point? So ice's normal melting point, water's normal melting point, is going to be 273 Kelvin because it's 0 degrees Celsius. So we would expect delta S to be equal to delta H over T. Delta H is given to us, and we know that the melting point of water is 273. So our answer here is going to be this one right here, and this would be a multiple choice question, so they wouldn't expect you to do all that math. They'll just give you the expression. Okay, so that brings us to probably our last major thing that we're going to go over in this unit, and that's the Nernst equation. So the Nernst equation has to do with concentration and delta G. So if we want to do delta G at pressures that aren't 1 atmosphere or concentrations that aren't 1 molar, we can use the Nernst equation. This is the Nernst equation. We don't need to know where this came from. You just need to know that it is a thing. It is not, I believe it is not actually written like this on your formula sheet, but in class we can go over how to derive this, not derive it, but how to pull this from your formula sheet. It's a pretty easy fix. So this is what the formula will be. Same formula as last slide. R is going to be the ideal gas constant. Now, when we talked about the ideal gas constant before, we've used the atmospheres one, which is 0.08206. This time we're going to use joules per mole Kelvin. So it's going to be 8.314 joules per mole Kelvin. Okay. Q is the same that Q was before. Right side over left side, or products over reactants raised to their equation coefficients. We did that ages ago, so you are familiar with that. If the temperature is at 298, you know that you can just look up on the tables delta G and then get the formula. Okay, so that's what this would be. If the temperature is something other than 298, then use this to calculate it. Okay, then you can use the Nernst equation to get non-standard pressure or concentration, because Q will take that into account, because Q will take pressures or concentration into account. Okay, so then you just plug it in. We've used the natural log before, but just so you have a little bit of reference in case you don't have a calculator here. Natural log or log for that matter, if it's a positive number, or it's always positive. If it's greater than 1, it's good. The log or natural log is going to be a positive number. If it is 1, the log or natural log will be 0. And if it's between 0 and 1, then it's going to be negative. So that's just something to keep in mind if you don't have a calculator on those types of multiple choice questions. Okay. So if the products increase, delta G is more positive, less thermodynamically favorable. If the reactants increase, delta G will be negative, more negative, excuse me. And that should say, and more thermodynamically favorable. So make sure you change that on your notes as well. Okay, so let's take a look at some questions here. Which of the following apply to any reaction that proceeds in a forward direction to form products from initial standard conditions? Okay. So this means that the reaction is thermodynamically favorable at standard conditions, so nothing about Nernst or anything. Okay. We know that delta G will always be negative if the reaction is favorable. We know that our equilibrium constant, this is from our equilibrium unit, will always be greater than 1. Remember, K or Q is always positive. But if the reaction favors the products, then our K will be greater than 1. Now, numbers 3 and 4, that goes back to our table we went over. They could be, it would depend on the temperature. Okay, so we're not going to say that it's always applies to any reaction. It could apply, but it doesn't necessarily apply. All right, let's talk a little bit about dissolving. This is just a little weird for some people. This isn't anything new. It's just something to think through. Okay, so use your thermodynamic table. You can look up the delta S's for this to see if it's favorable or not. Okay, so when you do that, and you look up Na plus, OH minus, I'm just going to do it real quick. Okay, so this is positive delta S, thermodynamically favorable, which is what you would expect for putting salt in water because it happens like pretty quickly, right? You put a salt in water, and this isn't NaCl, but NaOH, you put it in water, it's a salt, it's going to dissolve. So let's take a look at a different salt, MgCl2. If we do this one, and then we do 2 Cls, we get a negative delta S. So that's kind of weird, right? We would say, why is that? How is that thermodynamically unfavorable? Okay, it's still a salt dissolving in water. You would expect it to it would be favorable. So let's take a look at what's actually happening. So when you're doing the delta S calculation, which you just did by looking up on the table, you're not only looking at the ions breaking apart, you're also looking at the reactions between the H2O molecules and the salt, okay? While the salt definitely becomes more disordered, it spreads out, like it breaks up into its ions, right? So that's why you would expect it to be thermodynamically favorable. You would expect delta S to be positive, it breaks up. But the water does the opposite. So what will happen is that these negative charges will attract the positive hydrogens in the water molecule, and the positive charges will attract the negative oxygens in those water molecules. And so the water goes from just floating around wherever to being very ordered, okay? Because it starts attracting to those negative and positive ions. So the water is actually getting more ordered. And that's why the overall here is unfavorable. Okay, so when you look at this reaction, you would automatically think, oh, that's got to be more favorable. That's got to be favorable because it's splitting up. It's breaking apart. It's definitely more disordered. Okay, now this isn't something that you need to memorize, like, oh, magnesium chloride has an unfavorable delta S. You don't need to know that. What you should do is just, if you see this, be able to explain it, or don't let it throw you off, and don't always think that dissolving or dissociation is always favorable. Okay, so you just have to know that sometimes it's not. Oh, this is a repeat for something that we already saw. Okay, select the thermodynamic quantity below that is negative for any exothermic reaction. Exothermic means heat is released. So we know that delta H is negative, but none of the other stuff has to be negative for an exothermic reaction. It could be favorable, it could be not. So delta G could be positive, could be negative. It could be more disordered, it could be not. So delta S could be positive or negative. Volume, we have no idea what would happen just because it's thermodynamic. And K, it depends on what's favored, the reactants or the product. So all of that can be exothermic. Just delta H has to be negative. Select the thermodynamic quantity below that is always positive for spontaneous reactions. Okay. We know that delta G is always negative. Delta H can be positive, but it could be negative. Delta S, same thing. Delta V, same thing. K is always positive for every single reaction. Okay, the exponent on K, like times 10 to the negative whatever, that's okay. But you never have a negative actual value. Okay, it's always greater than 0. Sometimes it's a very small number. That exponent can be very negative. And that means it's not super favorable, but K is always positive no matter what. So what are these can be negative for spontaneous reactions? We just said K can never be negative, so we know that's not true. Delta G has to be negative if it's spontaneous. Delta H and delta S can be, and delta V, change in volume, can be. All right, so that's it for this video. You had some math thrown in there, some equations thrown in there, but it was mostly conceptual. So if you need to watch it again and think through these and pause the video, I think that's a great idea, because it is kind of hard sometimes for people to wrap their heads around these conceptual questions, and you will see them in multiple choice questions.